What do you want to talk about today? What's that?
Everything's apples to apples now. So if you do like one thing, everything.
We can cover absolutely any kind of problem that you want to try to cover. I'll try to segue it into the current stuff or previous stuff. What's up with that camera, man? A little glitch. A glitch in the matrix. It's glitchy. I do have examples that we didn't do in class, so I mean, those are a place to start. That one, that's one of them, definitely. We had, so I don't think I did this one. Is that true?
That's true.
And then I had this one right here. Didn't do that one. We might want to incorporate a stress concentration in there. So we had, we did that one, the simplest one. And then, as you mentioned, I had a different, I think I had a different thing you did. I tossed it. We had that one. All right, so get some things to choose from. Let's see, was there another one in here? No, I already assigned that one as the, right, that was the recoup one. I have a nice, what was that? Well, but the only difference is here is that in this example, as I tried to make it, I put in one of those things inside there. But this is the one we actually did. Right. So which ones do you want to do? We have that one, and we could in this. Did I do it? Yeah, I think I did. Here. This is a terrible way to secure a pin, but I put a stress concentration in there by putting a pin into the thing. So there's our choices. What do you think? This one? Okay. Something I haven't done, which I had meant to do in problems, I got to remember to do it, is because I don't want to give you an assignment or God forbid, an exam question and then not having asked this. But quite often I will tell you what the horsepower is and the RPM, and then not tell you what the load is. And I want you to be able to do that. That's a skill I want you to, it's a fundamental, I think, engineering thing, is to, if you're given the horsepower and the speed of something. So in this case, we have the kilowatts and the RPM. So from that, I want you to be able to figure out what the load is going to be. And also, well, this is sort of jumping the gun, but we're gonna talk about the pressure angle and how torque is made, right? So what we're going to get from this is that torque can be found from power and speed, right? That's a very, very important thing. So let's start from right there. And we could do that in our book, right? So I've already, maybe we should cover up the thing and pretend like we're starting right here. So, well, maybe I'll write out the problem right here. So I'm going to go. This is adapted from Beer Johnson's Mechanics of Materials. They gave this this view. It's kind of hard to tell because this is a printout right here of what's going on there. But essentially what we're looking for is these two gears on this shaft. So without bothering to try to make them look like gears, just make them look like wheels, we have sort of this arrangement right here. So we have a smaller gear up front. So it's very much like that recoup problem in what has to be done. So there's a bit of a review. we have these kinds of problems right here. And you can't see them here, but I'm suggesting these things have a hub, and we're not going to care about the width of the hub, but a gear will often have a piece like right there on it, right? So the shaft comes through here in this hub, and quite often there'll be the most common way, I would say that you want to, it's very common, is to have a keyway in there. And so you have a little piece, a little key, rectangular piece that fits into there, and then there'll be like a set screw that pushes down onto that. Does a pretty good job of keeping it in place along the axis of the shaft. But another way that you could do it, and this is a terrible way to do it, but I think maybe in pulleys, maybe you probably might see this, is they would drill a hole all the way through this, all the way, and they would put a pin in there. And sometimes they would put a tapered pin in, and that's even a worse way in some respects, but it could be done. They might also put this, like, sometimes, I'm trying to remember the name of it, but there's a type of pin that the cross section looks like this right here. It's got a little gap, and you could pound that into place, and it kind of acts like a spring and keeps itself into place, right? But anyway, the whole purpose for me is that I want to make a stress concentration and apply it in there. So we will go ahead and use the stress concentration types. There's only so many that in this book. There are lots of others, but this one has this stress concentration right here and this stress concentration right here. So that was my purpose in adapting this problem and putting a pin into these gears in this way, right? So let's see, let's go through the distances right here onto the thing and try to make it look halfway decent. So this is 120, 160, and 120. And they're showing the radius of these are 80 millimeter and 60 millimeter. So this is going to be 160 here, right? And 120 right there in millimeter diameters. And let's see, what else do we want? Did they tell us the determine the safety factors? Okay, the shaft has a diameter of 60 millimeters. And the yield strength is given as 120 megapascals. And the power, which, actually in our book we use capital H for power, but I always like the paragraph symbol for it. It looks like a P. I don't know what the H, I think they want to say that it's horsepower. Let's see, we'll go little n for the RPM, and it's 600 RPM. Now, we could, just from our knowledge of what we should have remembered from dynamics, hopefully, was that power is equal to torque times angular velocity. But, nicely for us, we can look this up in the book, which is, I finally put a tab in. So if you look into chapter 3, and here's for the United States, America, power. And they go ahead and they do the unit conversions to have torque times RPM. But we want SI, which is on the next page. All right, so here is the fundamental kind of concept here, but they're using radians per second. So if you want to instead adapt it for so if you want to find the torque, if you're given power, and important is that this is in watts, not kilowatts, and divided by RPM. So this is the equation that we want. This equation 344. It's a good one to bookmark these pages in here. This for me, depends on your edition, is 124 and 125. 124 here has the horsepower one with the 63,025, and here you have the equation 344 with the finding the torque from the watts. So we'll write that one down. So torque is going to be equal to 9.55 H over N. So 9.55, and we were given kilowatts, so that's 80,000, and divided by 600. And I think I have everything I need from here, except that I almost want to erase this so we can draw it out and you can see what's going on here. See a little bit better. That see, we'll zoom in. Okay, so if you can see, this gear right here is rotating this way. I'm showing it. Therefore, and for a free body diagram, we have to eliminate this. So that means that this is pushing upwards onto this gear. So up here, that's going to be that way, right there. So the torque is caused by that force, right? So if we're going to isolate, in order to see torque, we can't see torque until we cut the shaft. So I'm going to cut the shaft right here and then look at this gear by itself. And this, only the tangent one right here, and we can call this, I didn't label them yet. This is A, for some stupid reason they named it this way, but I think I kept it. So C, this is D, and this is B. Yeah, kind of dumb. But anyway, so we can call this is going to be our F, C, Y. All right, so the torque inside the shaft has to be the opposite direction from there. But because of the way the gears work, and I don't have one with me, I should probably bring it in there, there's always going to be a pressure angle. The actual force is going to come at an angle, which means that there's going to be another component right here. And we're going to call that FC Z, if I did the axes like I usually do. So we can find from the sum of the moments about the x-axis, I guess I'm not going to call it, we'd have FCY times the diameter of C divided by 2. That is that arm right there, right? And it's going clockwise, so it's minus, plus T. That's going to equal 0. So that's going to be FCY is equal to that torque that we just found. Oh, I didn't get the didn't bring my favorite calculator with me either. So 80,000 times 9.55 divided by 600, boom, it's going to be equal to 1,273 Newton meters. So for here, we go 1,273. And we're going to divide by the radius, which we know to be 80 millimeters. So 0.08. I think that's correct. Right, that's 80 millimeters in meters. So 0.08 divided. And we're going to get, like, I'm going to keep it in newtons. Maybe I'll go kilonewtons. Let's see. 15.92 kilonewtons. So I'm dividing by 1,000. And we can, now we have this, if we know the pressure angle, we can, I always have to think about this, right? We're going to rise over run, so we can multiply by the tangent. So FCZ is equal to FCY times the tangent of the pressure angle, which is often that symbol. So 15.92 times the tangent of 20 degrees, and let's load this one, equals, so 20 tangent times 5.793 kilonewtons. All right, I think, all right, so I'm going to go back up to here and draw this in right here. So now we need to find out what the loads on the other gear are going to be. So this thing has an arrangement so that this gear is going that way, so this gear is also going that way. So this gear is pushing that direction onto here. Therefore, that gear is pushing that direction onto this gear. But we could also, we really just want to know the arrangement, that this one is on top of that one. So it's going to look like, when we put both gears in place, we have this going on still, FCZ and FCY. If we're going to balance these things out, this thing has to be in that direction, which we could call FDZ. And that's going to be, this is the thing that balances it out. Think of it as hiding the torque inside the shaft, right? Because now we have to, summation the moments about X still needs to balance out to 0. Also, because of that 20 degrees, we're going to have an FDY going in that direction. And let's see, so I'm continuing on here. I'll have a minus FCY, CY, and it's going to be DC over 2. And then plus FDZ times DD over 2. The 2's cancel out, but doesn't matter. So we'll end up finding that FDZ is going to be equal to FCY DC over DD, which is going to be our 15.92, and then the DC I said was 160, and the units don't matter here because they're going to cancel out, 120. So 15.92, 160 times 120 divided. So we get 21.23, call it, kilonewtons. And then lastly, we could find our FDY is FDZ times the tangent of phi, or 21.23 times the tangent of 20 degrees. $7.726 kilonewtons. A lot of load crap. Stuff. I don't call it crap. It's good stuff. So I never drew up here the X and my Y and my Z into there. we want to take a look at that view and that view. So we're getting pretty good at this so far because we've done it through repetition. Hopefully it takes less time. It isn't nearly as painful as before. And all the little details of things that we might have missed at one point, we're not going to miss them again because we've gotten so much better at it. I think I didn't leave myself enough room to do all the work on this page, and you'd think I would learn better from my own mistakes, right? Better from that. But what can I say? Labeling this first task. We're going to, this one is the X, Y. I'm going to put my lengths in here, 120, while I'm thinking about it, while I remembered. And we're going to have F, CY, and then on top, we're going to have F, DY. So we're going to see that one and that one here and here. And then in the other view, here's our X, here's our Z, which is weird because we're looking that direction, but it's fine. So we're going to have, I made that way too close. I like to have these things. I'll move it down. It's going to be our F, C, Z. And then on this one, F, D, Z. It's going to be that direction, I think. Yeah, and this is the larger value compared to that. So maybe I'll write these in here so I don't have to keep looking back up. FCY was going to be is 15.92. FDY is 7.726 kilonewtons. This is FCZ is 5.793 kilonewtons, and FDZ is 21.23. So that's the big one. You almost predict that, like right here is probably where the moment is going to be the largest, but we don't 100% know that. But you could take a wild guess ahead of time, where we suspect. So let's do the first one on the left here. Some of the moments about, I guess, what are these? A, C, D, B. That's going to drive me nuts. Probably the hardest part of the problem. That they made some crazy damn thing. Okay, so we're going to go about A first, make it 0, some of the moments up there. So counterclockwise to start with, we got ourselves 15.92. We're going to use kilonewtons and millimeters. It doesn't matter because we're, all the units will cancel out. So if we start out with kilonewtons, we're going to find kilonewtons. I should have put in my guessed RBY. And what do you think? Should I make this one go ahead and make it downwards? We know it's going to be downwards, so let's go ahead and just put it in the direction that we know it has to be. RAY, right in there. And while we're here, we know this one over here for sure. This one's a little bit, it depends, this magnitude, how the numbers work. I've seen before where it was counterintuitive, but let's go ahead and make a guess and hope that we're right, of R-A-Z, Raz, is down that way. So back over to here, sorry about that. Counterclockwise times 120 It's going to be going clockwise. 7.726 times 120 plus 160 should be 280. And then this one is clockwise, counterclockwise, RBY is the thing we want to find. Oops, we need to multiply it by 120 plus that, right? So that makes it 300. So is it 400? And RBY is now going to be equal to, I could just read this off the page, couldn't I? But 726 280 times, subtract it, but it's negative, divide by 400. We don't get a lot here. This is a pretty small number. 0.6322. Maybe I ought to check my work with my previous answers here. Yep, that's what I got before. Kilonewtons. And then sum of the forces in the y direction equals 0. And I decided to go negative RAY plus 15.92 minus 7.726 plus 0.6322 equals 0. So let's see what we get for RAY. So we're going to get 15.92. I'm going to add it to that, and I'm going to subtract out that. Yeah, and I get, should be 8.826. Boy, that doesn't seem right to me. Nope, got the same thing before. All right, must be right. Interesting. Same thing over here for this guy. Repeating. Sum of the moments at A. I should have said this was A about Z. Now this is A about Y. Ooh, stomach just said it's going to come make commentary here. So this is going to be counterclockwise. So 5.793 120 minus, because it's clockwise, 21.23. I kind of think this might be too similar to the other problem. Well, whatever. I have to get a good variety of things. RBZ times 400 equals 0. So we get RBZ is 5.793 times 120, and then we'll subtract out 21.23 times 280. Boom. It's a negative value, so it's going to jump over there, so we got the right. And we end up with 13.12 kilonewtons. And then so the sum of the forces in the z direction, positively downwards, we'll say that this I chose to be in the positive direction, RAZ. So RAZ. Okay, so minus 5.793 plus 21.23 minus RBZ equals 0. Not RBZ. Oh no, I should write in the value. Sorry. 13.12. We just found that. So RAZ. Okay, so here is one where it ended up we chose wrong, right? So I just took a peek over at my thing, and so we said so we had to keep track of the signs correctly to identify that. So I'm going to take my 21.23, and I'm going to subtract out that 13 right there, and then I'm going to subtract out my 5.793. Boom. And I'm left with a positive number over here, but it has to jump over. So I end up finding with a negative 2.314 kilonewtons. So actually, that indicates I chose poorly. That it should have been upwards instead. RAZ. It's easy to get those wrong. It's easy to get them wrong. So let me walk through applying them. Now that I have the reactions, apply them to the shear diagram. Sometimes I do this too quickly, so let's make sure that we can do it. I don't want to just rush through it because this is where often mistakes get made right here. So we're going to come down with RAY. We know that that's 8.826. So I'm just going to pick something. I'm going to kind of try to scale it. It's going to be a negative 8.826. I put the units over here so I don't have to label the units in there. Now we're going to come up 15.92. So obviously it's going to cross the boundary into a positive number, and it's going to be right around 7-ish or so right there, right? So we could take that 15.92 and subtract out 8.826, and we get 7 point right here. 7.094. You feel comfortable with what we just did? Okay. And now we're going to subtract from that 7.094 7.726. And we get a negative 0.632. So pretty small right here. But that should match this right here, right? We're kind of making a double check of our statics. Negative 0.632. We could go on to the moment, but let's go ahead and do it over on this side too while we're in the shear mood, in the mood for shear. We're going to start here with the RAZ, which we said was 2.314 upwards. That's not a lot. And this is the negative direction because Z is actually pointing down, so we'll go negative 2.314. I'm micro writing now. And then this thing goes up, so it's actually adding to it 5.793. So 5.793 added to that, or subtracting from that, if you think of it as being a negative number. And so that's going to be negative 8.107. And then we're going to go down, or in this direction, was actually adding to that 21.23. And we should get a 13. So this is actually kind of substantial right there. A 13.12, which should match up with this reaction right there. So that's good news. Now we can go with the moments. And these are kilonewtons times millimeters, so we will get Newton meters. So we'll go 8.8 0.26, that says? I think so. And multiply it by 120. So you get 1,059, and that'll go this direction down here. So technically it's negative, so we'll keep it negative. Negative 1,059. Now we're going to add to that 7.094 times 160. Oops, damn it. I hit the wrong button. 094. I don't have an undo. Be a nice feature to have. If I wasn't using such an old calculator. Stop. So, that actually doesn't come up that's actually a pretty small value right to here. That's a 75.92. So it comes up there, but it crosses it as being positive right here. But we can actually check with this. It needs to come back to 0. So let's just go ahead and check it and say, what is 0.6312? 0.6312 times 120. Boom. It should be, and some of the decimal places fell off here because of round off error. But I get like 75.74. But it's going to go to 0. So you see, this is not a whole lot right there. Doing the same thing over here, we're going to take this 2.314, I think it says that, 2.314, and multiply it by 120. And we're going to get 277.7. And it's negative 277.7. But we're going to go in the same direction right here because this is also in the negative range. So it's going to go, we're actually going to subtract, but actually add. So 8.107 times 160 is the distance. And so we're going to increase that to negative 1,575. And then this needs to come back to 0. So we can also check it by taking that 13.12 and multiplying it by 120. Boom. And sure enough, we will, if we add that to this negative value, it will come back to 0. And our last thing to do as part of this is to get what the, no, I don't want to sum. I want to get what the total is at C. It's going to be the square root of 1,059 squared plus 277 squared if I did it correctly, I get 1,095 Newton meters. And then if I did over here at D, same deal, 75.92, which isn't going to have any effect on this really, and 1,575 squared. So we end up with 1,575 Newton meters. And I'm off by, on my page I have 4 written down, but it's just because this was 4 in my previous calculations because I dropped some sig figs along the way. But anyway, this is the max one. So this is the one that we would use with our calculations. So let's go ahead and, so this is the end of the loads section. We did all the loads up here. I didn't do any geometry section, so let's do a geometry. And so instead of just finding the area, we don't need the area in this case because we don't have any axial loads or transverse shears, so we don't need any areas. But let's go ahead and look in the book for the stress concentrations. That's always a good idea before doing the areas, because sometimes those stress concentrations are based on something else. And that is actually the case in this instance. I didn't remember that, but it turns out it is. So they decided not to put the information they needed in the caption. They went ahead and put it right here in this. So and it's kind of weird. They never even write out what this equation is supposed to be. And there's also some amount of confusion as to, should you use A or should you use B? Now, what do you think? I think you should use B, because we want to combine the stress, and that's where it would be taking place, on the outside fiber. But apparently they want to recognize that there's, for whatever reason, there's a stress concentration is actually larger there at A. I don't know why. And then they make an approximation of J over C. So what that means is when we go to, and they're using C for some stupid reason, even though this is torsion, you know that it's TR over J, so what we're going to do is we're going to divide torque by whatever we find right here. So that's going to be the base stress, though, and then we multiply it by our stress concentration. All right. Similar thing going on here in the moment for having drilled a hole. We have the moment divided by this whole thing, which is presumably the same thing as having I over C for right there. So the first things first, maybe we'll go ahead and get what our KT and our KTS are going to be based on this D over D ratio. So the D is the shaft of 60 millimeters. The D, I should have read the question mark. I made it. It's got a 6 millimeter hole. So I obviously was too lazy to make it. I made it easier for myself. So our big D. Is it big D over D or little d over big D? Yeah. Makes sense. We usually do a fraction. So 6 over 60. I could do that math. 0.1. So for the KTS is approximately, let me see what I said in the past to see if it agree. Do I agree with myself? So you got 0.1 right up in there, and here is 2.8. This must be 3.0 because it's 3.2, right? We must be counting by 2's to get to there and 2 to get to there. Okay, so here's 3, and we are almost exactly in between these two, right there, right? So 2.9, fair? So KT, we're almost crossing the intersection. We're very close to the intersection of 2.2. So close, I went ahead and said 2.2, but the fussy britches me might have thrown it a little bit of a, I don't know, a little nudge, like 2.22, just to be a jerk. But I already have the numbers down for 2.2, so we're going to stick with 2.2, but I might have given it ever so slightly, if I take my glasses off and I really zoom in there, really zoom in onto the thing, and and assuming it would be able to focus on its own. I don't think it can. Where did it go? I lost it. Right in there. I don't know. It's a pencil width. Not worry about it too much. So 2.2. Now we need this silliness. Let's write this thing down as we're in here. So we're going to go shear 0 is going to be T over. See, I can't get this in there at the same time. Can I? Let me see. I believe in myself. Okay. I can't get it without my hand in there. Pi d cubed over 16 minus little d, big D squared over 6. And while I'm here being silly, let's write this one down. We're going to go, can't do it. Nominal stress is going to be M over pi d cubed over 32 minus d over d squared over 6. So you really see that they're very much the same thing, right? Interesting that they're not, this is, as you would expect, one half of that, but this one is the same sort of thing. All right. Just shove some numbers in there. The torque we found to be, did we ever find it? Yeah, no, we found it at the very beginning, 1,273. Pi 0.06 cubed over 16 minus 0.006 times 0.06 squared over 6. And if you do that, and I did it correctly, you would get 95.12 megapascals. And in a similar thing, I'm going to go ahead and use my 1,570. I'm going to put I'll put the 5 in there, but I'm not going to recalculate it. Same deal. I mean, I don't know if there's educational value sometimes in writing all of these numbers out and wasting the time that it takes to do that. But I think sometimes there's little nuances that could trip you up, and so by showing you that I'm going to be thorough with it, you won't make those same mistakes. Maybe, I don't know. 196.9 megapascals. And I just screwed up. I'm sorry. These values are incorrect. I looked at my page. I skipped a step, and what I should have done, if I did this correctly, here you go. This is what, I'm going to fix it, but I don't know if you'll be able to fix it. But I can. Watch this. Tau is equal to KTS. Sigma is equal to KT times there. And then I'm going to put in my 2.9 and my 2.2. Is that okay? Yeah. Okay.
So, when you derive the shear equation?
Yeah.
And what is that? Is that just, that's just a modification to over J?
Yes.
Yeah.
Yeah. Yeah.
It's just weird to me.
It is weird. It is weird. No, it's weird, but it's what old man Peterson did. Old man Peterson, why did you do that to us? They put this thing in there, right there, and what they really mean is tau is equal to TR over J could also be written as J over C. Right? For whatever reason, this is the J over C that's right in there. All right, so now we do our usual shtick. This is a stress element that has, we're saying, right there, the worst case spot of 196.9 megapascals in tension or compression. It doesn't really matter, except that most of the time we're comparing to a strength that was tension. We assume for ductile materials they have the same strength in tension as compression. I don't know if that's 100% true all the time. It'd be interesting to actually experiment with that and find out. But in any quick case, this is what we're dealing with, and then we want to see if the thing breaks or not. So we want to use find both of them, the distortion energy theory, which is a lot easier. Got to find the von Mises. Square root of the normal stress plus 3 times tau squared. Because this is the case of uniaxial stress, we can do that. If it was a pressure vessel that had hoop stress, then it would have something here, right? But that's the only situation where that happens. So we get the 196.9 squared plus 3 times the 95.12 squared, and we get a 256.7 megapascal von Mises stress. And if you recall from the beginning of the problem, we said we had a strength of 160, so that would be no bueno. We broke. But it's a ductile material, so we might have actually been smarter to calculate von Mises without the stress concentrations, just to see, ductile material, maybe we don't need to compare that, because those stress concentrations were not. Although the stresses will be higher, so we would want to use those nominal ones because we did cut a hole in the thing. Right? It's not as strong now where you cut the hole. What am I doing? Oh yeah, so the maximum shear stress theory, we need to get the tau abs max, which we can take a shortcut and say we could take the normal stress divided by 2 and square that, so 196.9 divided by 2 squared plus the 95.12 squared, and we end up with a absolute shear of 136.9 megapascals. And now we have the either order we want to go these in. We take the yield strength and divide it by the von Mises to get the distortion energy value. And I did say it was 160, right? I can't. Was that? Really? That's terrible. Should have picked a lot larger. Because 256.7, we get, according to me, 0.47. Do I want to bother to go another sig fig? No. What's the point? I mean, there's no point. This is addressing how much factor we need to account for based on uncertainty, and we don't want to show how much certain we are about the uncertainty. Doesn't make any sense. Maximum shear stress theory, take it divided by 2, divided by the maximum. And sometimes we should probably say the abs max. Just to remind ourselves, there is a scenario that exists in which we would under-predict which is a dangerous thing, by if we only used one more circle. We need to use all three and find the absolute maximum. So here's 0.44, so it'll be less. That's a good problem, tough problem, tedious, long. Takes an hour to do.
So like this class, you actually incorporate everything that you made before, like you got it.
Yeah.
That's the point.
Want to repeat the thing, do the repetition, so then you're like, you own the thing. And it kind of stinks sometimes. It's tired. I'm so tired of 3D shafts. But that's an important piece of equipment inside a machine. You know, but also the details that you want to poke out. You know, gives us an opportunity to learn about, or to incorporate things like this fundamental relationship. As I've mentioned before, a lot of times in designing, one of the big uncertainties is load. This is actually here's an instance where load is fairly easy to find, although we have to remember that this is constant. This machine's going to start up. It's going to stop. You don't know what it's driving. It could be, it could be connected to something like a rock crusher. It's always my joke. I don't know if it's really a joke, right? Because you don't know what the load is. You don't know what the driving thing is. It could be a single-cylinder engine, so it's going to have this sputter, right? Its torque is going to fluctuate. It's not going to be this torque at that power. It's going to be large and then small and large and then small. There's uncertainty in all of the things that we're doing, but this is, in terms of like actually coming up with a magnitude, this is a fairly easy way to go, except one thing is you don't know all the time what the power is going to be. That just because the thing has got a much power of a motor, it doesn't use that much all the time. But then again, the torque isn't totally because of that. Like you could get like a rock that lands in your rock crusher that the rock crusher cannot crush, and all of a sudden jerk comes to a stop, and you're going to have a sudden torque that's going to be really large. And now your shaft breaks, right? So there's these uncertainties that we're dealing with, and that's just one of the many ones. And we will address those, though, along the way. Sometimes what you do is you apply a factor. And sometimes those factors just seem like they come out of thin air. But if you start looking at enough factors, you can kind of get an idea. All right, here's how, and they're all about the apples to apples. We have what's on this piece of paper, and then we have the real world, and we're trying to make those the same thing. All right. We good?